Welcome back to the shop. Today we got a technical one. We're talking about the valve train and cylinder heads for my twin turbo LS7 build. But first, let me show you a little bit of the new jewelry in the engine compartment. Check this out. So with the engine block off to the machine shop, had a little bit of time with the cylinder heads and the top end to mock it up on the old long block and put together this new turbo kit. So in the previous video, I took delivery of this new intake manifold, which is a significant departure from the vertical inlet intake I removed. So this required that I completely redo the cold side of the turbo piping, but since the exhaust was going to remain the same, I was able to use it like a jig to build a new turbo kit right on the engine stand, which made things super easy. Aluminum is super pleasant to work with. It cuts and shapes with ease, and welding shiny new tubing is always a satisfying experience. So overall, I'm pretty happy with how this turned out. Here's the finished product. It should comfortably fit under the flat hood, and I'm pretty happy with the look. Little feature to add. Support for some nitrous jets. Thinking right there. Single jet NOS, baby. So I machined up this little bung on the lathe, and this will be the inlet point for the nitrous jet. Nozzle port there on the bottom, and just to see what we're working with on the inside, there is the inlet port. And here we go, the completed look. Most of the plumbing's in place too, so we kind of get a sense for the layout of things, but yeah, pretty happy with how it turned out, and again, should fit comfortably under the hood. Now with that, I've implemented a few other changes. Still running the Aeromotive 12 gallon per minute mechanical fuel pump, now with number 12 or 3/4 inch fuel line, full 3/4 inch number 12 fuel rails with a number 12 crossover, and out to new style Aeromotive fuel pressure regulator, which is shorter, more compact, again to fit under the flat hood, and then the number 10 return all the way to the back of the car. Now with the updates to the fuel system and the turbo kit, so you can see the oil cooler fitted right here behind the bumper. I designed and printed a nylon duct which ducts air from the factory opening point in the Nova bumper. And you can see there the ducting right into the Setrab oil cooler there. So nice to have front-facing airflow to provide a little additional cooling to the engine, given the fact that the radiator is in the back, tucked in nicely just in front of the wastegate there. And to make servicing the engine, pulling it in and out a bit easier without losing all the oil all the time, added these two Jiffy Tight quick connects. These are like a dry brake fitting, meaning they disconnect and they reconnect without losing any fluid. Now this particular design is a full flow design, meaning there's no internal restriction through the dry brake portion of the fitting, which means it provides the same rate of flow through the fitting junction that it does in the rest of the line. This is half of a nylon printed bracket I made, and I'll show that a little bit in some of the other footage on the bench, what that's like. And on the LS engine, where we take off is in the factory location for the oil cooler. So simply an adapter block here that takes off feed and return to and from the engine, and also that's the point where I take off oil supply for the turbochargers. So again, feed and return coming off the block, routed up through the quick connects and out to and from the oil cooler. By design, that oil cooler should dissipate several thousand BTUs of additional heat energy from the engine, which effectively augments the cooling system. So with my radiator in the back of the car, long drives on the street, particularly if I'm running gasoline and not alcohol fuel, especially at highway speed when the air shooting under the back of the car doesn't really duct up enough into the radiator. So I'm hoping that this front-facing oil cooler will provide additional means of cooling the engine because of the fact that oil itself is one of the primary coolants in the engine besides the water. Cylinder heads for the twin-turbo LS7. So like other areas in this car, I've looked to professional motorsports for not only inspiration, but also for part selection and design inputs for maximum performance and also reliability. Now, the GM LS engine platform has been used in a variety of different motorsports, but most notably in the ARCA series NASCAR, which is basically a stock car style racing series with a spec engine. Now, Ilmor Engine Manufacturing in the US produces the sealed crate engines for the ARCA Series NASCARs. And those use an LS7 style cylinder head, similar to this one here. Spec camshaft and valvetrain assembly that's been designed, engineered, and tested for maximum reliability under those racing conditions. And those conditions are high sustained RPM, 7,000 to 8,000 RPM for hundreds of laps, and to do so with a long service life. Although this is the GM LS7 cylinder head casting, the hardware and valvetrain is directly from this NASCAR series. So, a couple key differences. First thing to note, compared to the valvetrain that's currently in the car, NASCAR LS7s use a single beehive style valve spring. Now, this differs from the dual spring, and the key features on a beehive spring are, as you can see, the variable diameter in the winds, which affect the resonant frequencies in the spring. And basically this lends itself to stability characteristics in the spring at high engine speeds. Now, some advantages of the beehive are it can be tuned to be extremely stable with lesser spring rate, meaning it does not simply have to rely on spring stiffness to control the valve train at high engine speeds. Now, it's also lighter weight. And when it comes to the valve train, the forces involved in the valve train and the wear and tear on parts are directly proportional to the mass in it. So with a lightweight titanium intake valve, that means you need less total spring pressure to manage that. The beehive spring, given its less weight, also really lends itself to valve train stability in that application. So in addition to the titanium intake valve, tool steel retainer for strength, which another key feature of the beehive spring is the retainer side is smaller in diameter than the pocket side, which means that the retainer itself can be smaller and lighter weight, which is a sweet combo. The LS7 cylinder head, unlike most other LS heads, uses a pedestal system for the rocker arms. You can see these pedestals here, where rockers mount individually on cast-in pedestals on the cylinder head. Now, this differs from many other LS heads. You can see here, where many other LS heads have flat machine pads where a cast rocker bar will be bolted on below the rockers. That cast one-piece rocker bar does lend itself to stiffening the attachment points between rockers, and at high engine speeds and with high spring pressure can help with stability. But the LS7 doesn't have it. Under extreme racing conditions, there's a little adjustment that's made. Okay, so you can see here the cast-in mounting for the rocker arms. Many aftermarket castings and racing applications move to a one-piece billet rocker bar. So the benefit of this rocker bar is it replaces these cast-in stands with a one-piece design that when all the rockers are bolted down, tie them all together and make an integral assembly. It really improves the stability in the valve train mounting in each of those attachment points for the rockers by tying the assembly together. But the only problem is these heads have pedestals cast in. So we got to head to the milling machine to modify this. One additional feature is this will also allow us to adjust the height and the position and effectively manipulate the geometry of the rocker arm relative to the valve tip. So that's an important detail in optimizing the rocker travel as it relates to the valve stem. So having adjustment in the rocker height is a critical feature and an added bonus to moving to the one-piece rocker bar. Let's head to the welding table. I'll show you one more that we're working on. Although I got an awesome deal on these LS7 cylinder heads, they did sustain a little bit of damage here due to a drop valve. I've started by removing the intake valve seat. To do that, I basically welded a nut to a washer and welded that assembly in and pulled that out with a slide hammer. Not the most elegant way, but it's my first time doing it, so that was a learning experience. The cylinder head guys would have had a bit more finesse in doing so, but nonetheless was able to get that seat out, clear the space, and basically assess rest of the damage in the chamber. Now, fortunately, the exhaust seat is perfect, and the chamber really hasn't sustained a tremendous amount of damage. The rest of the holes look really, really good. Now, the short block itself, actually just the engine block, is at the machine shop, and we'll be heading there. But in the meantime, we'll work on the custom camshaft. So we'll talk a little bit about camshaft theory and kind of my approach to speccing the camshaft for this application. With the camshaft spec will come the valve spring, the rest of that package, setting up rocker geometry. Hopefully we'll have a long block together soon. So got most of the damage in chamber 1 welded up. Same with chamber 2, had a couple tiny little debris nicks in it, so went ahead and touched those up with a little bit of filler. Until next time, thanks for staying up to date on the twin turbo LS7 build, and spring is right around the corner, so we got to get busy. Also, more race car stuff under the cover.